So the gradient and the directional derivative. Previously, we've talked about basically the definition and how to calculate them. Now I want to start talking about some of their properties and applications. So the first thing I want to talk about is finding the max and min directional derivative. So for the directional derivative, we can make some additional statements about it using dot product properties. So we have this formula that the directional derivative of the function f in direction of unit vector u is just grad f dot u. But we know properties of dot products, that is just the magnitude of the gradient of f times the magnitude of u times cosine theta. But we already said u is a unit vector, so this is just the magnitude of grad f times cos theta, where theta is the angle between these two vectors, grad f and u. So first of all, this gives us an alternate way to calculate a directional derivative. That's the first thing. Second thing is it lets us say some things about the directional derivative. When will the directional derivative be largest? Well, it's going to be largest when cosine theta equals biggest possible value is 1. So when cosine theta is 1, so when theta equals 0. Well, what does it mean for the angle between them to be 0? It means they're pointing in the same direction. So from this we can conclude the direction of the greatest rate of change is the direction of the gradient vector grad f. And that's just got to be always true. And furthermore, what is the largest value for the directional derivative or the rate of change at a point? The magnitude of the greatest rate of change is the magnitude of grad f, the magnitude of the gradient vector. So it turns out that the gradient vector is the magical vector we talked about before. It is the vector with that points in the direction of the greatest rate of change and whose magnitude is the greatest rate of change at any point. And then furthermore, the directional derivative clearly is going to be a minimum when theta equals pi, meaning that grad f and u are in opposite directions. And at that point, that minimum value is negative of the absolute value of magnitude of grad f. And then also we can observe that when the vectors rather in the same direction or opposite direction, what about if they're perpendicular? Well, if they're perpendicular, then cosine, so then theta would be either pi over 2 or 3 pi over 2. Cosine of that is 0. Therefore, the directional derivative of the rate of change would be 0. So we've learned some properties about, while trying to figure out some properties of directional derivative, we actually found some properties of the gradient vector. So now we've got all these things together, let's apply this to a problem. So for f of xy equals x times ln y, and we're at the point 2, 1, first of all, we're going to find grad f. So grad f equals, first we need a df dx, which is just ln y, then we need df dy, which is x over y. And then let's look at grad f at our point. So grad f at the point 2, 1. So plug it in and you get 0, 2. Okay. So next, at our point, what is the greatest rate of change? So the greatest rate of change is simply the magnitude of the gradient vector.
Let me actually write that directly. The max rate is always the magnitude of the gradient vector, which in this case is just the magnitude of 0, 2. So work that out and you just get 2. And then what is the unit vector in the direction of the greatest rate of change? So just to abbreviate, I'll call that the maximum direction. So we know that the gradient vector points in the direction of the greatest rate of change, and that's 0, 2. This question is specifically asking for the unit vector in that direction. So in order to get that, we've got to divide by the magnitude. So times 1 over 2. So you just get 0, 1. So there's the unit vector that points in the direction of the greatest rate of change. Okay. And then, new type of question. What is the directional derivative in the direction pi over 6 from the gradient direction? So notice that in this case, we're not being given a vector per se, but we are being given is an angle. So the way that we can solve this is with the new formula for directional derivative that we've developed using the properties of dot product. So we know that the directional derivative can be written as the magnitude of the gradient times cosine theta, where theta is the angle between the direction and the gradient. So in this case, magnitude of the gradient of f, we know that at our point, we know is 2, and cosine theta is just cosine pi over 6. So that's 2 times rad 3 over 2, which of course is just rad 3. And if you want an approximate value, that's about 1.7. Okay. So this is how we can answer new types of questions about other aspects of the problem using directional derivatives and gradients. Okay. So a couple of comments on some of the things that we figured out here. So we defined gradient of f as df dx and df comma df dy, and then we proved that it points in the direction of the greatest rate, and its magnitude is the greatest rate. It's also possible to do it the other way. What we could have defined the gradient of f as the vector with those two properties, and then from that figured out what its formula would be. That's just an interesting side. Okay. So now we go on to another aspect. It turns out there's a relationship between the gradient vector and level curves. This is going to be another property. So let's take a look. So if we imagine that we have, first of all, the function z equals f of x, y, we know that the graph of that requires, well, x, y, and z, so it requires 3 dimensions. Now, from this, we could also have level curves. So a level curve would have the equation f of x, y equals c. That formula only has 2 variables in it. That could be graphed in 2 dimensions. So furthermore, note that in the direction along, meaning parallel to a level curve, the function is not changing. That's what it means to be on a level curve. The value of the function is going to stay at c. So if we reinterpret that, what should that mean? So therefore, that should mean that a derivative in that direction is 0. So in other words, the derivative of f in that specific function u should be 0. But we also know that a directional derivative is just the gradient of f dot u. So therefore, that must mean in this scenario that grad f dot u, where u is pointing, where u is tangent to the level curve, so grad f dot u must be 0. But we also know that if the dot product of two vectors is 0, then they must be perpendicular. So this tells us that for when u is tangent to the level curve, then it's going to be perpendicular to the gradient of f. So the gradient vector, which also points in the direction of the greatest rate, and level curves, which point in the direction of rate equals 0, if you like, these are perpendicular. So now let's apply this to a problem. Okay, so we've got the function which gives us a surface from the function f of xy equals y minus e to the x. So first, let's graph the level curve at f equals 0, and then we're going to find the gradient grad f. Let's do some introduce ourselves to what's going on here. So first of all, what we've got is z equals y minus e to the x. So if we want the level curve at f equals 0, what we're really saying is 0 equals y minus e to the x. Well, we can rewrite this in a way that makes it very familiar. This is just the same as saying y equals e to the x. So our level curve is really just y equals e to the x. So let's graph that. Okay. Let's say we've got, there's 1, 2, 3, 1, 2, 3, looking like that. We know this curve is going, oops. Okay. So something like this. We know that this is the curve y equals e to the x, and this is specifically the level curve for f equals 0. Now let's calculate the gradient. So the gradient of f equals, so df dx, negative e to the x, df dy is just 1. Now let's go ahead and find, so part C asks, find each normal vector on this level curve for x equals 0, 1, and 2. Okay, now, how do we find something perpendicular to a level curve? What we just found is that the gradient is perpendicular to the level curve. So this represents the level curve. The gradient will be perpendicular to it. So gradient of f at x equals 0, just plug it in and you get negative 1, 1. The gradient of f at x equals 1, it's going to be negative e, 1. And then the gradient of f at x equals 2, it's going to be negative e squared, 1. Negative e squared is like about negative 8. Okay. So now, so we found the gradient in each of those points. What we're claiming is that each of those should be perpendicular to the level curve at its point? Well, let's take a look. Let's identify those points. So I've already marked where x equals 0. Let me also mark where x equals 1. Let's go higher. And let me also mark where x equals 2. That's going to be up here. This is a sketch. It's very approximate. Okay, so at that first point where x equals 0, let's draw in the vector -1, 1. So at this point, vector -1, 1 looks something like that. Now, give or take my amazing drawing ability, does that look reasonably like it's perpendicular to the level curve? Looks pretty close. Looks pretty good. Now next, at the point where x equals 1, let's draw in the vector -e, 1. And again, -e is about, -2.7. So from that point, -2.71, let me move, oops. Forgive my technical difficulties, 1 second. Okay, maybe I'll just erase it and rewrite it so it's not in the way. Okay. Okay, so this point, -2.7 and then 1 is something like that. Again, it's an approximation. Does that plausibly look like it could be perpendicular to the level curve? Yeah, it's pretty good. And then finally, at the point where x equals 2, -8, 1, that's looking something like this. And again, that plausibly, give or take my amazing drawing ability, perpendicular to the level curve at that point. Yeah, that's certainly plausible. Okay. So there you go. So notice that we found, so that answers part C. For a level curve, we can now find a normal vector at any point. It's just the gradient of the original function at that point. So now bonus, find a parallel or a tangent vector to the level curve at x equals 1. This is part D. So notice that at x equals 1, the perpendicular vector is -e1. Well, in 2 dimensions, we know how to turn a perpendicular vector into a parallel vector. You just switch them and then make one of them negative. So 1e, and in fact, let's draw that in and check it out. So at the point x equals 1, drawing in the vector 1e looks something like, 1e looks something like that. And reasonably speaking, that does look parallel, meaning tangent to the level curve. Okay, so that is what we can do where we originally have z equals f of xy. So the original graph is 3-dimensional, but when we take a level curve, that's going to be 2-dimensional. And then that level curve, we now know how to find normal vectors. We just need the gradient of the original function. Now we're going to kick it up a notch. And by that I mean we're going to kick it up a dimension. So if we have the equation g of x, y, z equals 0, that's a makes a 3-dimensional graph, and its gradient is a 3-dimensional vector, and the vector will be perpendicular to the surface. Why is that? The reason is this equation is a level curve for the function w equals g of x, y, z. So note that formula has 4 variables in it, so its graph would actually live in 4 dimensions. We're not going to visualize that, but it's important to keep track of what is your original function versus what is your level curve. And remember what you're taking the gradient of and what is perpendicular to what. Let's see how this works with an example. So, for the surface xyz equals 12, let's find the equation of the normal line at the point 2, negative 2, negative 3. Okay. So in order to find the equation of the normal line, in order to find the equation of any line, what do we need? We need a point and a direction vector. We're given a point, so we need to find a direction vector. We need a direction vector for the normal line. In other words, we need a normal vector. So, in order to find the normal vector, we need a function, then a level curve, and then we take the gradient. So, what is the function? The function is xyz, and that's equal to 12. So remember in our original, so that's a level curve. Let me just say that. So f of xyz, f of x comma y comma z equals xyz. That's the function. Xyz equals 12 is a level curve of that. So when we take the gradient of f, it will be perpendicular to the equation xyz equals 12, the level curve. So gradient of f equals, in this case, there's three variables, so f sub x, f sub y, f sub z. And calculating that, pretty straightforward. It's going to be yz comma xz comma xy. Now, of course, we don't just need the formula for the gradient, we need specifically the gradient at our point. So the gradient at our point, 2, negative 2, negative 3, is, just plugging it in, like this, calculating, doing the arithmetic, we get 6 comma negative 6 comma negative 4. So now we've got we've got our point, 2, negative 2, negative 3, and our direction, which is our perpendicular direction, 6, negative 6, perpendicular to the surface. So there's our direction vector. So now we can combine that into the equation of a line. So writing it the usual way, xyz equals 2, negative 2, negative 3, plus our parameter t times 6, negative 4, or we can write it using the symmetric form. And also, just to give a graphical understanding to what's going on here, here is the graph on the right side. So here I've graphed the surface, or at least part of the surface. And then I've also put in, you can see the green line is the normal line, and where it sort of ends on the surface, that's where it intersects the surface. So that is the point 2, negative 2, negative 3, and then it's continuing in the direction of our perpendicular vector that we found, 6, negative 6, negative 4. So again, I want to emphasize the initial step of identifying what is your function, and then what is your level curve of that, and then the gradient of the function is perpendicular to the level curve. Oops. And another comment, since we now have, relative to the surface, to the original surface, we have a point and a normal vector, it's now also very easy to write down the equation of the tangent plane. And so this actually, using the gradient, actually represents an alternate method to find the equation of the tangent plane. And a very nice one at that. Let's do another example. So find a perpendicular vector to this surface, 0 equals 4 minus x squared minus y squared minus z squared, at the point 0.5, 0.5, rad 3.5. So we've got a surface, and we need to find a perpendicular vector. So notice that this equation represents a level curve for a particular function. So that function is xyz equals 4 minus x squared minus y squared minus z squared. So now we can just find, the gradient. So the gradient of f equals negative 2x, negative 2y, negative 2z. But of course we want the gradient at our point. So the gradient at our point is, and now we just plug in, negative 1, negative 1, negative 2, rad 3.5. And because we've got the gradient to the gradient of an original function, and our surface is the level curve of that function, our gradient is perpendicular to that level curve surface. So there's a perpendicular vector. Okay, so those are some of the problems that we can do using these new properties of the gradient and also the directional derivative. There's one particular thing I want to point out, which is what happens when we kick it up a dimension, kick it down a dimension in terms of finding these normal vectors. So I just want to finish up this little section by saying a word about that. So I want to say all these things. It's a lot of words, but I just want to reiterate the point. So if you have z equals negative 3x plus 2y, that's written as a function. 2 inputs, 1 output. That's going to be graphed in 3 dimensions. So the gradient is going to have the inputs x and y, so the gradient vector is going to be 2-dimensional. It's going to have 2 components, and that's going to sit in the domain. On the other hand, if you write 0 equals negative 3x plus 2y, that's written as a level curve. Again, this has 2 variables, and again, it's going to be graphed in 2 dimensions. And the gradient, just of the stuff on the right side taken as a function, is going to be perpendicular to this level curve graph. Now, w equals 3x minus 2y plus z, that's written as a function with 3 inputs and 1 output. That's going to be graphed in 4 dimensions. And the gradient with 3 components will be in the domain of that function. On the other hand, writing 0 equals 3x minus 2y plus z, that's written as a level curve. So that has a total of 3 variables. So that's going to be graphed in 3 dimensions, and the gradient with 3 components will be perpendicular to the graph. Those are kind of the problems that we worked on so far. But now let's point out where the confusion might occur. The first case and the last case can be confused with each other. They both have 3 letters. And in fact, it's the exact same equation. Z equals negative 3x plus 2y is algebraically equivalent to writing 0 equals 3x minus 2y plus z. So, is the gradient tangent to the graph, or is it perpendicular to the graph? And the answer is it depends on which quote-unquote gradient one takes. So if you have z equals negative 3x plus 2y, if you treat it as a function of 2 variables, then the gradient has 2 components, and it's in the domain. On the other hand, suppose you treat it as a level curve of a 3-variable function. Then the gradient grad w is going to have 3 components, and that's going to be perpendicular to the level curve, which is what we thought of as the original graph. So what does that mean for doing problems? If you're given z equals f of xy, the graph is a surface. It's physically 2-dimensional. We graph it in 3 dimensions. So treat it as a function of 2 variables, unless you need a vector that is perpendicular to the surface. Oops. In that case, rewrite it as g of xyz equals f of xy minus z,
and now it equals 0. And that converts it to a level curve of a function of 3 variables. So again, to understand this relationship and this connection, it's important to keep in mind, are you thinking of your original equation as a function, or are you thinking of your original equation as a level curve? Just to put it all together, here's a quick summary of all the things, a short summary of the things that we've done recently. Okay. And just to finish up, let me just mention that I said a lot of words, but hopefully this is something you can refer back to as you're doing problems. And doing problems, working on examples is really the best way to get familiar with what am I taking the gradient of, what do I think of as my function, what do I think of as my level curve, and depends on what you're being asked to do. And you just have to get used to it by seeing different examples, different problems, and working through.